When training language models, we want them to process a sequence of tokens and then predict the following word. However, when we apply them to rescore some decoding output, they need to deal with errors and still predict the correct following word. In this paper, we propose to teach the language models to do so by means of data augmentation. We need to deal with the three cases of ASR errors. So when we want to introduce a substitution, we simply substitute the input token. When we want to delete the input token, we instead delete the whole time step. Finally, if we want to emulate an insertion, we insert an error news token and we carry over the target token. The real question is, how exactly do we get these errors? And we compare several options here. We have the zerogram model, where we only tune the overall rate of substitutions, insertions and deletions, but apart from that, we sample the errors uniformly across the vocabulary. We compare the zerogram model with a much more powerful unigram model, where we actually collect statistics from transcriptions of training data to learn what words are likely to get replaced by what is likely to get deleted or inserted. And of course, we compare this with an oracle model where we collect the statistics from the development data. We evaluate our augmentation on Chime, where we use a Kaldi system as the baseline for the first pass decoding. Our language model is an LSTM and we use it for N-best rescoring. The results. We were really surprised to see the zerogram perform the best. The unigram error model, which we had high hopes for, actually performs the same as the baseline. Even if we provide the actual statistics on the development data, it's quite hopeless. And these characteristics translate rather well into real test data. So our paper presents a simple augmentation scheme for language models. This augmentation brings significant improvements. On Chime, we nearly doubled the improvement from second pass rescoring. Additionally, in our paper, we compare these input augmenting schemes with target augmentation. We discuss the stability and predictive power of perplexity under this augmentation scheme. We also show how this improved on different data, which is not so difficult. We discuss where do these improvements come from. Is it just regularization, or do we really learn the distribution of ASR errors? And last but not least, we show a sensible defaults for the input zerogram model so that anybody can just use it even for their language models.